So now we are basically asking, so just to recap slightly as to what I said before lunch. So we are now at the case where the answer to the original question, does there exist a seeding that would allow W to win, that would allow V star to win, the answer to that question is no. Okay. So now the modified question is there a way to fix some matches that would enable V star to win, right? And we sort of agreed that if I am allowed to change log n, n being the number of players, okay, you can call it m, I guess, number of players, then log, if I am allowed to change the outcomes of log n number of matches, then there exists a way to ensure that V star wins. So now the question is, can I do in less than log n? Specifically, if I am given a value L, L is the number of arcs I am allowed to reverse, or rather the games that I am allowed to fix. For this given value of L, does there exist an SBA such that L arcs have been reversed and that the new graph, the new win-lose graph has an SBA rooted at V star. Okay, so that's the question we are asking. All right. So the input is the win-lose graph, and the input also comes with the value L, for instance, and so we are asking whether there exists a seeding that would enable the favorite player to win. Here also we assume that we have So you remember the affected set, that these are the players that are participating in those upset matches. Okay, so the same thing holds. Suppose, assume that we have this. So it turns out that this question can be, just to give the sort of ending away, right, like movie in a flashback. So it turns out we can answer this question in 2 to the power n poly n time. So look, first and foremost, I probably should say why this problem is hard. It should be easy for you to see, because if the original problem was hard, just finding a seeding without any reversal of arcs, that tells me for arbitrary value of L, which is the question that I am asking now, that if I am not allowed to bribe anybody, the question was hard. That was the content of the previous talk. So for an arbitrary value of L, the problem can only be more harder, right? Because it's a more general question. So the hardness prevails here for this question. So this is why we assume that, okay, the best we can do is an exponential time algorithm. This is a single exponential time algorithm. So you can see, so that if you are wondering why I have written it this way, 2 power n into polynomial in n, poly n should be subsumed by that thing. It is basically to emphasize as to that there is basically you have to sort of make 2 to the power n number of choices, and so this poly n, this is sort of a matter of this is where the main work is done, and this is sort of some amount of bookkeeping and so on and so forth. Okay, so this is I just wanted to mention that, because if you are wondering why it's been written separately, it's because of this. And of course, this is the time complexity, and this is poly n is the amount of space taken. Okay, so okay, and another algorithm that we can give answers this question in 2 to the power ordered k log k poly n time. So this basically makes this is the same time complexity as our original problem, right? And why? And this is because basically we solve this problem by reducing it to the instance of our original problem, and then we use that algorithm. Okay, so this reduction from this problem to the problem where no bribery is allowed, that takes no more than this much amount of time, and then we invoke our that previous algorithm, and we know that is the time complexity. This is the time complexity for that algorithm, and therefore the whole problem can be solved in 2 power ordered k log k poly n. Okay. All right. So before I start before I sort of go into the algorithm, I will first describe some properties, okay, some structural properties we will explore. Using those because those properties hold, okay, using those, we utilize those properties to design the algorithm. So if I just tell you the algorithm, it will make absolutely no sense, but once you know these properties, then it will make sense as to what we are doing, why we are doing. So obfuscation means basically when you're hiding something, you're trying to sort of prevent. So these are after all manipulation problems, right? Like somebody is manipulating, somebody is trying to do something underhanded thing. So you don't generally want outsiders to know about it. So you want to hide that as much as possible. So in that way, I'll be defining a couple of operations that we perform on the SBA. And they can be viewed as some kind of obfuscation operations, like you're basically trying to hide the matches that you're trying to fix and so on. Okay, so the first operation would be called subtree cleanup, and the second one is called cyclic shift. So we say an operation is valid. Okay, so an operation will take in an SBA. Okay, it says if it is valid if it returns a subset. So in this case, we are assuming that not import. We have, so the win-loss graph D, correct? We have our favorite player V star. We have the number of arcs we can switch, the arcs we can reverse, number of arcs this, as well as a set of arcs, let's say R. So R is subset of the arcs in this win-loss graph D, okay? And the size of R is at most L. So this is the thing. Suppose we have this set R, okay? We are going to say that an operation is valid. So this operation works on B and R. So B is the SBA given to me, okay? And I have the subset R of vert edges whose direction has been switched. So if those vertices, if those edges appear in B, then they appear in the reversed form. Is that clear? So of course, every vertex incident on any edge in R will appear in B, because B is a spanning tree, right? So every vertex has to appear. But there is no reason why every vertex sort of, this edge, so if an edge in R is present in B, you must read it as like it is present in its reverse form, okay? But R has been defined as a subset of edges in the original diagram of D. Okay, so you'll see why this sort of thing is sort of important, like as we go through it. So an operation is said to be valid if it returns some subset R prime. This is also a subset of edges, okay, which is of size at most L, and the new SBA B prime, okay, rooted at V star. This is that guy V star favorite, says that only the arcs in R prime are reversed. So in B, only the arcs in R were reversed, right? And after doing a valid operation, I will obtain another B prime, another SBA, in which the root remains the same. So in B also the root is a favorite, okay, same thing. And here also the root will remain the same, but the subset of arcs reversed may be different. So R prime can be different from R, okay, but the size of R prime cannot exceed L. Is this clear what valid operation means? So if you can sort of see ahead, what's going on is that we will take an SBA, okay, make some modifications to it, okay, and obtain another SBA which satisfies this property, okay. So what would that mean? What would that mean? So if I started out with an SBA which was rooted at V star, contains no more than L reversed arcs, that is a valid solution for my problem, right? That I am allowed to reverse L arcs and V star should be the SBA. Then I am saying that by doing these operations, I am creating another SBA. There also the root remains the same, the number of reverse arcs does not exceed L, but perhaps the arcs I do reverse is different. And why do I care about this? Because maybe the way I reverse arcs in R prime has lot of structure to it, and knowing that structure can help me design the algorithm, okay. So that's the idea. So basically what we will do is start with an arbitrary SBA rooted at V star, suppose such an SBA exists. By doing these valid operations, I can convert that one step at a time to another SBA, okay, where I have a very sort of a precise characterization of the set of arcs that has been reversed and other aspects of the tree. and that type of an SBA is the one that I will be looking for. Because if the original SBA existed, then this must also exist, and so on, if and only if. So answering the original question would sort of boil down to finding the SBA with all these structures. Okay, so that's the goal of these operations. So the subtree cleanup operation. Okay, so this is the topological order, or that rank order. So these edges, this one, okay, I'll just color them red. So I was going to draw these things by hand, then I realized I'm not doing a good job of drawing here. So I took the liberty of copying these diagrams from our paper. Okay, so these are red arcs, you can see, right? No. Okay, so all the missing arcs are the forward arcs, from left to right arcs. So these are the upset outcomes, right? Because a higher rank player C is being beaten by a lesser player V, right? So these are the upset arcs. So this is the topological ordering, and suppose this is the example, this is the SBA I have, okay? And this is the B prime I will. So the blue arcs are the one that represent the reversed arcs, okay? So between V and U, okay, if you see here, the order of the arc direction between V and U is U beats V, correct? That's what I said, because U appears before and there is no arc going back, so U beats V. But here, clearly we have switched the order, we have switched the direction, right? So similarly for blue, this one, okay, I don't know, this is as W, it should be star, let's just say V star, okay? Notational inconsistency, sorry. So if there is a confusion, please do ask, okay? Don't get lost in all these notational inconsistencies. So from now V star to A, I see that, okay, between V star to A, again A beats V star, but here we have switched the order and V star is beating A. So these are the only, and rest you can check that all are fine. So here basically L is equal to 2, all right. So when is this operation used? It is used when V star has a child, okay, on whom the subtree contains a blue arc. In other words, when all the blue arcs, meaning the reversed arcs, are not incident on V star, only then do I perform this subtree cleanup operation, okay? Do you understand what I am saying? When you have a situation like this, that there exists a blue arc in this SBA, but it is not incident on V star. This blue arc involves V and U. So this is the time, this is the thing, this is the situation where I would sort of perform the subtree cleanup operation. This arc, as you can see, is fine. One of its endpoints is V star, the other one is A. This is fine. This arc is not the reason I am performing the subtree cleanup operation, okay? So how do we perform this operation? So I go down the tree and zero in on the subtree on which the blue arc is incident. So we always have the arc pointing downwards. So I look at the root of the subtree where the blue arc is pointing from the root to one of its children. So that would be this subtree, correct? Bad drawing, but okay, you get the picture. So I just look at the vertices in this subtree. So let's call it TV because it is incident, it is sort of on V. And I look at the subset of vertices that appear here. So that is the set V of TV, okay. Now I look at the induced subgraph in the win-loss graph on only these set of vertices, okay. So in this subgraph, in this induced subgraph, I do not have any reversed edges. This is where it's the original win-loss graph, okay. This means that induced subgraph. So from here, so I take this subtournament, I find any SBA in this, does not matter who the root is, and arbitrarily I sort of I create an SBA, okay. This can be done like just do a depth first search sort of a thing, and you can do this. Doing so, I replace, so from here I find a T hat U, let's say, okay. This is the SBA on sort of SBA in this D of, let's call it something V of TV. Okay, this is this thing. Instead of this, I pluck out this subtree and replace, oh, it's also using U here, so I did not see that. So instead of this subtree, I replace it with this subtree. Okay, you will see that the set of vertices appearing in this subtree and this subtree are identical. That is by construction, because I only looked the SBA that I found was from this SBA in this subgraph, which only consists of vertices from this subtree. So I basically possibly this t hat of u, this is this thing, I replace this. Okay. Now I do one other check. Now u has become the root of this subtree, correct? Now I go back and check, is v star u a part is an arc in the win-loss graph? If it is actually part of the win-loss, if it is an arc in the win-loss graph, okay, meaning this v star actually beats u, that's the question I am asking, right? So in this particular, if that is the case, then I do nothing, I just add an edge between v star and u, because this edge already exists in the graph, right, in the graph D. However, for this specific example, we see that, well, v star and u actually beats v star, right, in this graph. So then, if I wanted to make u a child of v star, I need to flip this edge. So this is why I change r prime, remember I had a set r consisting of these two blue edges, right? Now I define r prime. Can you guess what should be my r prime? R prime should tell me the set of reversed arcs in this SBA. This should give you some hint. No? What did I do here? What all reversed arcs what did I change here? I said I just basically moved, see, this was a blue arc because we needed to beat u, right? I created I replaced this subtree with another subtree that already exists in my original win-lose graph. So what that means is, I am not allowing any blue arc to appear in this subtree. Do you agree? I basically got rid of this blue arc, because I don't have to, I just found some vertex u to become the root of this thing, and I replaced it with this. So now how can I change my, what should be the new blue set in this SBA? So is it not the case that, look at the blue edges in this subtree. They no longer exist, right? So then remove all them. So take from R, remove all the blue edges that existed in this subtree. So that is this set, right? R minus ATV will tell you that all the blue edges that exist outside of this. And I take union of u of v star if this is the edge that, so basically if in the original graph D, such as in this example, if u is beating v star, then this is the edge, now this is the edge that I will now flip. So I add this to my R prime set. At the very least, so what happened here? So basically I made this switch because there was a blue edge here, right? By removing this blue edge and replacing with a blue free portion here, and adding maybe at most one blue edge here, I have reduced, what I have done is, maybe if there was exactly one blue edge here, then here also I have the same number of blue edges in this B prime. But if this subtree had more than one blue edge, then I have effectively actually reduced the number of blue edges also, right? Because now there are no blue edges here, there is just one blue edge incident on the root of this thing. So the size of R prime is at still L, right? I did not exceed my size, correct? Because this one this is at least size 1, so this is L minus 1, at most L minus 1, and I am adding at most 1 edge. So this is still L, this is still an SBA because I did not mess with my root, everything's remained the same. So this is the valid operation. This is what we call a subtree cleanup, okay? So what happens with subtree cleanup is, any time this property is satisfied that there exists at least one blue edge that is not incident on my V star vertex, I perform this operation again and again. Doing it as many times as needed will give me a SBA in which the blue edges are all incident on V star. So can you tell me what this means in sort of realistic term, as in terms of the tournament fixing problem featuring players and so on? What does this mean? See, at the beginning we started out by saying that in the seeding it's a very sort of how you fix the seeding is a rather complex question, like what seeding would favor V star, because in that original example at the very beginning when we saw briefly, like it does, who you play in each round, okay, is determined by who plays whom in the other matches, right? Because when you move from round I to I plus 1, okay, who all won round I will determine who you will play in I plus 1, right? So it is not absurd to think that in order to rig the tournament in favor of my favorite player, it might need me to actually fix games that involve other players. Because if I knew there were certain opponents that are particularly easy for me to beat, for my team to beat, then I can just ensure that only those people win, and therefore I will always have an easy path to this thing. That is what this SBA was doing. But what we are saying is, by the valid subtree clean operation, we note that if there exists a solution of this kind, then there also exists a solution that requires me to only fix matches involving my favorite team. Okay? That is the outcome. So then what this does is sort of narrows the number of possibilities I need to check. As long as I know who will play against my favorite team, okay, my favorite team, and then I know who I have to fix and so on. So sort of this seems to give more structure on what all matches to fix. Okay, the next property is what we call the cyclic shift property. Now in this case, so here the topological ordering is the natural, so V1 first followed by V2, V3, okay, so like this V4 and so on. So this is an incomplete tree, just the portion that is relevant to us has been described. So obviously this has what, 23 words, it will have, you basically will complete this in sort of make it an SBA. So this is the part where the sort of thing that is relevant to us is happening. So in this case, what this topological order means is that V2 in the topological order, V1 appears before V2. Okay, V1 is nowhere to be found here in this example. So before V6, okay, so let me just write this here. So V1 doesn't actually appear. So V2 is the first thing. V5, V3 also does not appear. Okay, V4. Okay, V2, V4. V5, V6, V7, V8, V9, V11 and V23. Okay, so just sort of this is the topological ordering that we are looking at. Okay, so the blue edges are the ones that are the reversed edges. Okay, so why are the reversed edges? See, in terms of this topological ordering, V4 should beat V6, right? Because this is how it goes. So here these are all unaffected vertices, assuming that these are all the sort of a non-upset vertices. Okay, so all arcs are going from left to right. So V4 should be beating V6, But here we see that actually that match has been rigged, that match has been fixed, and then again V11 and V5, clearly V5 beats V11, but that game has also been fixed. Okay, so this is the situation. So here now, okay, so the example here is this thing. Okay, so let me just, okay, so I perform this operation. It is performed when I have a path, subpath, okay, from P1. Okay, so I should give a definition first actually. Okay, sorry, I should have introduced a definition before. So let's just okay, let's just see here first. Okay, all right. So suppose this is the example that we had for the graph D. Okay, I'll just introduce a small definition and then we'll come back and complete that operation. I'm sorry, I just forgot that I should have said that before. So this is the graph that we were looking at. This is suppose the topological ordering. Okay, so these are the black edges are the normal regular edges, the red edges are these upset matchups. So in this case, we will define this thing called type. Okay, so we identify where all these affected vertices sit. These are the ones. Okay, now I look at the whole ordering and break it into these chunks. So look at the first affected vertex that appears in the topological order. Okay, that has type 2. If there are any unaffected vertices that appear before it, they are called type 1. If this set is empty, meaning the first vertex that appears in my set is an affected vertex, then this does not exist, and that vertex itself is a type 1 vertex. Okay, so this is the way I sort of split this thing. So the next so it's possible that between C and D there were other vertices which were unaffected vertices. They would have type 3, and then again when I see so basically the whole topological order is broken into these chunks. These are the unaffected vertices, these are the affected vertices, these are the unaffected, so this way. Okay, so because we have k affected vertices, correct, we assume that k is the number of sort of affected set. Notice that there can be k plus 1 types. Do you see why? Because between these affected vertices there are k minus 1 gaps. There is one gap at the front, and then of course there is one gap at suppose this is the last thing. So they are basically, they can have k plus 1 types. Okay, this is what I mean by a type. Okay, so now let's just go back to this thing previous. Okay, so I apply the cyclic shift operation if I have this particular path in my SBA. So this is B, again I have R, the blue edges, and this is here LS2. Okay, so this is P1 to PQ. They have, this is a path that exists in this tree, okay, in this SBA. They all have same type. Okay, let's call it type I. Is it fine? So basically, if I look at that this topological order, it means that if I is greater than 1, okay, so it means that strictly greater than 1, that this is the block within which these vertices appear. These vertices are all from outside of, they are unaffected vertices. Okay, so they are from the set. This means that they are not the affected vertices, and they all sit in one of these blocks. So this is the I minus 1th type. This is the affected vertex which has type I minus 1, and it's followed by another affected vertex which is of type I. Okay, so P1 to PQ is of this kind. All right. Furthermore, see in this set there can be many vertices, right? So all I am saying is from between P, this, if I look at the subtournament induced on only these subset of vertices, that is an acyclic subtournament. Do you agree? There are no cycles here because all the arcs are going left to right. So it is not, so conceivably it's possible that in this large set I pick out some q vertices which sort of appear from left to right, but that not necessarily they are not like consecutive, but we require that here. This is basically that P1, P2, PQ, they appear consecutively, okay. So here also. Is this clear? So this, I need this property as well. So basically they will appear, this P1 to PQ appears in a block. Furthermore, I also need that there exists P0, okay, same type, and it is the player that is immediately preceding P1 in the topological order. So I will write it as preceding P1, okay. Preceding means with respect to the topological ordering. See, P0 is not part of this path P, okay. Any questions so far? So lots of properties, lots of things to check, okay. Now they are of the same type, either the whole block of the same type must have the same relative ordering with x and y, because x and y have a different type. No, so because these are unaffected, the type I vertices, the one that appeared in like a bunch of them, because they are unaffected, at least the ones that we are talking about, yes, because they do not have any back arcs. So if one of them, that's a very important property used in the proof, that if one of them is an in neighbor of x, all of them is an in neighbor of x, and opposite is also true if one of them is an out neighbor. So for types, vertices of the same type, you can say this. And the reason why every affected vertex has a unique type is because this relationship does not hold for them, because you are allowing back arcs and all. The adjacency relationships between two different affected vertex, it cannot be captured that way. When we say that multiple vertices have of the same type, what we are basically saying is they are sort of equivalent vis-a-vis their out neighbors and in neighbors. That's precisely, that's a very good question, okay, that what's actually happening. That's the thing that we are trying to zero in on, okay. So now P0 is this vertex that precedes P1 in this sort of topological order, has the same type, but P0 is not the parent of P1 in this SBA, okay. Lots of properties to see, so let's just see the example what I'm trying to say. So this is V5 is P0, okay. P1 is say V6, V7 could be, yeah, okay, right. So yeah, so these are all these edges sort of going through, okay. Now can you say, do you like by the properties that I listed right now, right, do you think that P will have any blue arcs, meaning are any of these arcs in P reversed? Because P is a path in this graph, in this SBA. So I said nothing about blue arcs per se, like explicitly I didn't say anything. I said P is a path, so it could have blue arcs, right? So the question is, can it have blue arcs, or can it not have, like do you see what's sort of going on? See, because I said that P1 to PQ is not only a path in this graph, but P1 to PQ are consecutive vertices in the topological ordering, and they have type what? They have the same type, right? So meaning what? That they are like in between two affected vertices. In between, they are a directed acyclic graph. This path that it appears here also appears in the topological, this ordering, the same ordering holds in the topological order. This topological order is on the original graph, the win-loss graph, which does not have reversed edges. Therefore, P, this path cannot have any reversed edges. So, it is a blue free path. Okay? That is kind of important. Okay? So, this is the situation. So, this is P1, P2, P3. If you look here, that V6, 7, 8, this is the type, sorry, no, not this one. So, in this case, because none of the affected vertices are mentioned, we can assume that all of them are of the same type. Okay, like all of them, like meaning they are all unaffected vertices, so they are like they are not affected vertices, so this thing. So, okay, so this is V5, V6, V7. So, V5 is the parent P0 which appears before V6, see before P1, but V5 is not the parent of P1 of V6 in this graph, because the parent of V6 is V2. This is the situation in which I can sort of perform cyclic shift. So, now can you guess what happens? What I am going to do is say that I am going to move P0. P0 is a parent of V6 which is my current P1, right. My path starts at P1. I will make an adjustment that I will force P0 to be part of this path, and P1, P2 and other things will appear, but obviously if I want to keep the same length, PQ, which is the last vertex, it will no longer be part of the same path of the same length, because P0 is now being inserted. So, PQ will basically take on the position of P0. Okay. So, if you look here, this is what is happening. V5 becomes the parent. I already know there exists an arc between V5 and V6 in this order, because this is the this is told to me by this property, that P1 is the precedes P0. So, from this I know that from my diagram from this topological order and the fact that I have the win-loss graph, this edge P0 to P1 exists. So, this edge is the one that this is it. So, this is that P0 to P1 edge. Okay. So, then P1 to P2 edge is this thing, that remains the same, it has just moved one level, right. Now, P2 to P3, this is the last edge, basically PQ minus 1 to PQ, this last edge that appears in this path P, that no longer exists in this SBA, because V8 has taken on the position of V5. So, if you see V8 appears in the original position of V5, this is what this is, and V5 has now become the parent of P1. Okay. Now, now I ask you, well, if just by making V5 can very well become the parent of V6 and take on the subtree, and then we move V8 from down below, but what happens to the other edges? Why, like what is the relationship between this new P0 which is sitting here and all the other subtrees to like the other children of the original P1? Can you say why, like do you see what the relationship will be? What is the relation, what is happening here between remember these are of the same type, right. So, what is the relationship between V6 and V11 and V11 and V5? No? So, okay. So, in this example, it is sort of clear to see that if V6 is the pair is an in neighbor of V11, meaning if there is an arc going from V6 to V11, because these are all the vertices of the same type, V5 is even a stronger player than V6. This is a acyclic, this portion of the, if I look at the subtournament here, this is an acyclic subtournament. So, if V6 was beating V11, V5 will also beat V11. So, this edge was not, this edge that we have V5 to V11 was not used in this SBA, but it exists in my original graph D. So this is, I add this. This is a non-reversed edge, correct? Now it's possible that there were, now on P1, think about all the, so what is happening is basically that the number of reversed edges incident on any of these vertices in P, okay, say on Pi, the same number of reversed edges is incident now on Pi plus 1. So the number of edges that was blue edges that was incident on P1, okay, the first vertex in this path is going to be is the same number of edges that are incident on this current first vertex in this path, which is that the P0 vertex. So if I add up like this, I will see that the number of reversed edges, the blue edges that were incident on any, if I take all of them in total, the number of reversed edges incident on any of these vertices taken together is the same as the number of reversed edges incident on the vertices in this new path P prime that I have replaced in place of, that I have put in place of P. Okay. So that's basically, this is why this number of the L does not change, that the L, whatever the L value was here remains the same. Now however, can you say what the what the R prime set should be? See, this R prime set, all I have said is the number of reverse arcs does not change, but R prime has actually changed. Can you see why? In this example at least. Okay. Okay, if this is hard to figure out, or can you tell me what R prime should be? I have told you that, well, R prime and R can have R prime cannot exceed the size, the value L. In this particular case, it is exactly, it remains the same size of R and R prime, but R prime can, if we do this operation by, it will not exceed the value L if R was, assuming R was at most L. So now, can you say that if this is how I create, that I will force P0 to be the parent of this P1 in this particular new SBA, and whoever was the original parent of P1 here will now become the parent of P0, okay. Then can I classify what my this number of reversed edges should be in this graph? Note, I said P0 is the parent of P1 in this topological order, meaning in the original graph D. So whoever was the parent of P1 in this SBA can only be a vertex even more stronger than P0, correct? So because of this subtournament, acyclic subtournament property, I know that this edge that I am adding V2 to V5, this cannot be a reversed edge. This edge actually exists in D, right? So here I am not going to spend any, I am not going to have to reverse edges. So where is the reversal of edges actually happening? So, okay. So I can just say that if this is all I did, that I am just going to move P0 to the top of P1 and move down, and PQ at the end gets attached to V5. I know these two operations I can do. Now in the worst case, what can happen is when PQ gets joined, PQ takes the position of P0, right? This might be a red arc, and this might be a blue arc. This is a possibility because I have no information as to who the parent of P0 is in this thing and what its relationship is with PQ. So in the worst case, it's possible that this arc actually has to be reversed, right? So I can say that basically take all those edges that are, create the tree like this, and after you have created this tree, so remove, basically see who all are there, the edges that you need, the oriented edges that you need to make this into an SB, like a downward pointing tree, and see, so look at this set, this is basically the reverse set, meaning look at the set of edges that appear in T prime, right, in this thing, and basically look at those that do not appear in AD. That is the reverse set. And by the counting argument we have seen whatever r prime might be, the size cannot exceed r, right. So, therefore, this is again a valid operation. So, I spent a lot of time doing this because I will basically use this these two operations to show that there exists a solution. If there exists a solution to a problem, there exists a solution to a problem which utilizes these two properties. Okay. So, now we move on to this notion of elite players. Okay. So, you understand the notion of types now, obviously. This slide should have come before. Yeah. So, this is type 1, this is type 2, this is type 3, this is type 4, 5, 6 and this is, yeah, these are unaffected vertices. So, they are type 6. Okay. So, here we define a subset of vertices or players is said to be an elite club if this particular property holds true. Every player in this set beats my favorite player. Okay. So, here the favorite player is marked as the star. So, every of them has to beat this player, this guy. Okay. So, interestingly what happened, okay, all right. So, then followed by the fact that if you take, for example, if this is a type 1 vertex, set of type 1 vertices, okay. If B is part of the set S, then every vertex that is of the same type as B but appears before B, meaning appears to the left of B, must also be included in the elite club. Okay. So, I am looking, so basically what it means is if you pick a vertex of a certain type, every vertex stronger than that, right, who is of the same type must also be in this club. So, this is what the second property means. So, we will show that, okay, in this example, the elite club would be A, B, C, D. Okay, so C and D are affected vertices. Okay, they are individually of type 2 and type 3. You can always pick them to be part of your elite club. But if I pick B, then A must also be part of the club, or else you cannot call it an elite club. Okay, so basically A, B, C, D, these are the the members of this elite club. Okay. So, now we can show, okay, that if there exists an SBA rooted at V star containing L number of blue edges, meaning reverse edges, then there exists an SBA rooted at V star in which all the blue edges are incident on my V star, meaning you just look at V star and all its children, all the blue edges will basically involve V star and one of its L of its children. There are no other blue edges in the rest of the string. That is what this first property means. Furthermore, so I know by this property that V star is one of the endpoints of this blue edges, right. So, I should probably change this color. V star is the root of this thing. So, of course, the edge has to be pointing downwards. The question is who sits on the other side of the blue edges. It turns out these are only the members of an elite club. So, there exists an elite club such that this property, all blue edges go between V star and member of an elite club. Okay. So, if I could somehow get my hands on an elite club, then what would happen is that I would know that how to sort of rig I would find L of them and just sort of rig the match. So, that sort of gives me a way to think forward as to what can happen, right. Okay. Okay, and why do I say that? Basically because if I know which matches to fix, I basically switch the direction of the arc and then pose my original question. Does there exist an SBA rooted at V star, right? Because now it's reduced to the original question that we discussed in the previous talk. Okay. So, these are the properties that are used by our algorithm. Now, the question is why do these properties hold? This property can be shown to hold by repeatedly applying that subtree cleanup operation. You keep on sort of applying that operation and the blue edges basically move one level up, and you keep on doing it until all the blue edges are incident on V star. Okay, and again successively applying that this cyclic shift operation basically allows you to show this property that the blue edges, okay, will only involve members of the elite club. Okay, all right. Okay, so I am going to skip this proof and just assume that this property holds, okay, and show what sort of lies in store. Okay, I'll just assume these two things are true. Now, using those two properties, we can actually show a couple of nice structural properties that basically inform that are used very crucially in the algorithm. Specifically, if the win-lose graph is acyclic, okay. So remember, when the graph was acyclic, our previous question, where does there exist an SBA rooted at V star, that was easy to answer, right? So assuming that answer is no, now I am asking, the graph is acyclic, but you are allowed to switch L arcs, okay. Now, can you answer that question? Like, is there a way to create an SBA rooted at V star? Is it clear what we are saying when we say the win-lose graph is acyclic and posing this question? It turns out that favorite can actually win this where L arcs have been reversed if and only if there exists some such set of players. There exists at least this many players that favorite actually beats, and this beat means in the original graph D, like without bribing. Okay, this part means without bribery, meaning these arcs are like V star to this arc, non-blue arcs. Okay, so let's okay, so let's just see why this is true. Can you tell why this might be true? Like, can you see why something like this might hold? See, the graph is acyclic, okay? Okay, so let's just do this. So favorite can win with L reversed arcs, right? So it says that there exists an SBA V star where there exists an SBA with V star with blue arcs somewhere in that L blue arcs in somewhere in the SBA, correct? Now, using our previous property, we know that if such an SBA exists, then there also exists an SBA rooted at V star where each of those L blue arcs are incident on V star, correct? So all these blue arcs are the ones that basically are the reversed arcs, and they are all incident to V star, right? So now I say that, okay, so if whoever these L arcs are, I know that V star is the root of this tree. So V star has how many children? Log n children, right? N being the number of vertices in the graph. So of the log n children, L of these are the ones that have blue arcs incident on them. So look at these other non-blue neighbors of blue children of V star. Okay, these are the ones. So do you agree, if in this subtree, in this graph, if I am sort of write it this way, that these are, say, the L blue children, and these are, I want another color, black. No. I haven't gotten the hang of this yet. Okay. Okay. These are the non-reversed children. Is it okay? Do you follow? So these are the children on whom the sort of this arcs have been reversed. They are all pointing downwards. These are this thing. Okay. So because of the size property of those of the SBA, do you remember the size property? We said that they always have to be power of 2. There is a child who has size 1, meaning 2 to the power 0. There is a child, the subtree is of size 2 power 1. Then there is a child with subtree of size 2 power 2, and so on and so forth. So we know that if I look at all those children, that are blue, sort of the ones that do not have a blue arc incident on them, and sort of sum up their size. Okay. So, in the worst case, this will be how much? So, at least, so see, this is like a very pessimistic count, because I am basically saying, imagine that the smallest subtree, which is like a one child like one vertex subtree, is one of the blue. I do not know where the blue and the black are, they might be always scrambled. I do not know. I am saying that at least the number of the number of vertices that this sort of the total vertices that appear inside the subtrees of the children of V star which do not have a blue arc, they must at least be this much, correct? This is like the smallest possible thing. So, then what does this sum up to? Isn't this precisely this value? Right? Do you agree? So, this is just a simple summation. Now, so basically this says that, so if these are the reversed arcs, okay, so this is, so now can you sort of see why this property can hold? Yeah, I'm sort of proving the forward implication. But the fact that this subtree, this is not subtree, this is a collection of subtrees, right? This is the child and V star is sort of their common parent. These have size at least n by 2 to the power L minus 1, right? These vertices are, remember there are no blue arcs here, correct? So, these are all forward moving arcs from left to right. This entire subtree only has, these subtrees only have black arcs, meaning this is the original D arc. Furthermore, each of their root, each of these subtrees that we have, each of their roots are beaten by V star in the original graph, correct? So, basically if I look at the induced subtournament involving the vertices in this set X and V star, I get a directed acyclic tournament, subtournament, where V star is the unique winner, right? So, then I know that V star base. So, when the moment I have a directed acyclic tournament where V star is the unique winner, basically it means that if I were to have if I look restricted the topological ordering only to these vertices, V star would be the source, meaning V star would be beating all these people. So, that basically proves the forward direction, right? This is a constructive proof. I exhibited to you precisely who are the people. Not precisely, at least this many people. V star would also possibly beat lots of people here in this subtree, but these are the people. So, I need to prove just this, right. So, this is the forward direction. So, in the reverse direction, if I just knew favorite only beats this many players, can I actually create a subtree? Can I actually create an SBA with at most L reversed arcs, meaning L blue arcs, such that V star is the root? So, the forward direction, so this reverse direction is where the thing is. Suppose I have this set, okay, again I am going to call this X, okay, this is the set X. I know favorite beats these people. So, if I were to create a if I were to create, okay, so let us see. So, I am going to look at this set this, okay, and partition this set. Can you tell what I do? Partition this set into subsets, of course disjoint subsets, okay, of size, again we are again playing with size. Use this formula, this should tell you. I'm trying to find another example where maybe this can be shown. Okay, no, I don't have. Yeah? No. I was just seeing if there's an example here in the paper where, yeah, tell me. It's the same thing. So I basically use this number of vertices. I know this is the size. I will create a set. Okay, I should use U0. Okay, I create a subset x0, x1 all the way to x log n minus n. If x is it is strictly bigger than this, basically remove some vertices arbitrarily, always create an x, split this entire set into this sort of thing, okay, just the set x, where x0 size, each of their size would be basically 2 power I. This formula, because this sums up to this, tells me that this is possible. X has size at least this, so I can create this thing, correct? However, like using these subset of vertices, create some SBA involving these vertices. Does not matter who the root is, okay? I know no matter who the root is, V star will always beat those people because V beats all of them, right? So basically you create these subtrees like this, each of increasing size, their root, and basically V star is each of their children, okay? And the rest of this set that exists, which is the rest of the set P minus X or D of like vertices in D minus X, create again the other SBAs from of size, say whatever the remaining size is, does not matter who the parent is, because they are only, see over here I have created log n minus L SBA. So over here involving these many players, you basically create, I am writing all over the place, L SBAs of appropriate size, right? So whoever this thing is, you basically will make this V star will beat this. Basically I'm going to force, whether or not V star beats this person, in reality it does not matter. I can always switch this arcs, there are only L of them, correct? And over here I have the sort of log n minus L of these things which are from the set X. So I know V star always beats them. So this is, so I have basically created an SBA where V star is the root and only L edges are reversed. Okay? Is it clear? So it's basically just the numbers game. This is why the structure of SBA is so important, because we have all these size values. I know exactly how to split this thing. I know this V star beats, whoever wins, this can be created arbitrarily, and I know that it will cost me no blue edges in this portion of the tree. The blue edges will only be incident on the parents of this. Whoever is the root here in these subtree doesn't matter, because V star can be forced to be, can be made to beat them. Okay. So this is for acyclic graph. Now tell me, where did I use the acyclicity property? You were not paying attention. So in the forward direction, when I was arguing this case, the fact that V star, the fact that you have these edges here, right? These edges, these are all black edges, right? So meaning these are all the original edge. So if V star beats the parent of V star beats the root of this subtree, it means V star, because there are no cycles in this graph, it means V star sits to the left of these vertices, each of these roots. So if this guy beats this its child, which it does because it's a black edge, it means V star must also beat this. So because V star beats each of these roots of these subtrees, it means V star beats everybody here. So in this forward direction, I use the fact that it's a DAG very crucially. If I did not have that property, I could not have shown this. Now for when it's not a DAG, then also we can say something. We still have an if and only if condition, but it's slightly a little more relaxed sort of. Okay. So what does this mean? That you can have an SBA with L reversed arcs, at most L blue arcs, if and only if there exists a set of players U, okay, of the same size, notice, but now we are not saying that, we are not requiring that V star beats all of them, but instead what are we saying, that there exists a seeding, because this may not actually hold true, like it's, this is harder to say, this is a lesser of a, this is a more vague condition. We are saying there exists a seeding on this that makes favorite win. So there exists a seeding, meaning if I only looked at this subset of players and I considered that question, that there exists an SBA, okay, on this subset of vertices with V star as the root, and none of the blue arcs, by the way. This is the original, it's an SBA in the original graph. This is an if and only if condition. And if you think a little bit, you will see that so what happened in the previous case when I was drawing here, instead of explicitly telling you exactly precisely how I am going to, sort of doing this partitioning thing, if I only had the guarantee that these vertices X union V star has a subseeding among themselves, which will ensure that V star wins, then this whole thing goes through, right? So that's why that having this property is enough for this one direction. The question is, in the other direction, what do I do? So I say that in this direction it's clear what happened, because this is the part that is given to me for free, that favorite wins, and whatever the other players are, which would be the subtrees, the other subtree, which would be the log, the L remaining subtree. These vertices would account for the log n minus L number of subtrees, right? There are total of log n subtrees. For the other log n subtree, for the other L subtrees, because I am allowed to have L reverse arcs, I can basically use the reverse arcs on the root of that and make V star win. So this condition is true. In this forward direction, can you say what will it be? I say it's even more straightforward, because you have this L reverse arcs, that there are only, and I'm using the fact that all these L reverse arcs are obviously just sort of incident on V star and one of its children. So basically what we are saying is there are L children of V star on whom the roots of which are the other endpoint of the blue arcs, right? So if I start with that SBA, that particular SBA, and then what do I say? The rest of the SBA, that the one that does not have any blue arcs, they have black edges, like they are the unreversed edges, right? And the unreversed edges, so they are the edges that appear in the original graph D. Now I no longer have the acyclicity property. However, what can I say? Okay, so I'll just have to move forward a little bit, because I need to use these things to get to my algorithm. So I'll just leave it to you. If you think a bit about this, it's again a counting argument, so it works. Okay. Okay. So all right. So then, okay. Now see, this thing is obviously this holds. Now if favorite actually beats all these players, it's not that there exists a seeding that V star can win. This property, that there exists a seeding that V star can win, does not require V star to beat everybody. But if V star could actually beat all of those people, then of course it's even a better situation, right? So this is the acyclic situation that is not needed or holds for this non-acyclic case. Okay. So, all right. So now, to get to my algorithm, I am going to define one other form of like maybe I think this is the last definition. Okay, so you are given an SBA, okay, of size n. We say we define an L-removed binomial arborescence, SBA, okay. So I'll draw here. So you have, say, a vertex R, and you have all of its children, V1, V2, and all the way to log n, right? Okay. Now, so this log n, so look, so they have been arranged in the order of the smallest subtree to the largest subtree. So this is a subtree of size 1, okay. This is a subtree of V2 has a subtree of size 2, and so on, and this has a subtree of size n by 2, okay. So that's the thing. Now suppose, so now this L-removed arborescence with respect to this SBAT is one where you basically delete these edges. The last L edges, these are L different L arcs, so all representing edges going from root to its children. So I am saying that delete the last L such arcs. So what you would have is a disconnected graph, right? You have root and it is connected, still connected to its first log n minus L children, and you have bunch of other L subtrees, the roots of which are not connected to the R, okay. So this is what I will define an L-removed binomial arborescence. Like the close attention should be paid to the fact that I remove the last L people, the last L subtrees. I remove those edges, not like any L any of the L edges, okay. Interestingly, it turns out that favorite can actually win with L reversed arcs if and only if this win-loss graph actually contains a SBA which is L removed and of course rooted at the favorite. So this is, so what does this mean? This says there exists some SBA, okay, where L of the arcs are reversed. By applying that previous property, I can assume even that the SBA that this is, the L reversed arcs are all incident on V star, right? Okay, so this thing tells me that there are some L reversed arcs. I can even assume that L arcs are incident on V star, correct? So V star is the root and you have these L arcs. But it does not tell me which L arcs, right? It could be the first, it could be the 10th, it could be any L arcs could be reversed, right? This tells me, no, if there exists such a way that there are only L arcs reversed, well then there also exists a solution in which the last L arcs are incident to the last L arcs are the blue arcs. So do you see, so this, if just because this is true, it's not at all clear why this condition also should be true. So now if this is true, this side is obviously implying that, right? That if the last L arcs are removed, okay, add those L arcs, maybe the worst, always add those arcs as V star pointing downwards to them. Maybe all of them would have to be blue arcs because they don't exist in the graph, but that will give you an SBA with L arcs removed, right? But this direction is the part that is the thing. So suppose this is true. Let's assume for now that this is actually true, okay? We'll maybe come back and do the see the sketch of the proof. Now can you define and now can you think of an algorithm? Is this result clear, what I am saying? That because of this, we actually have, so if you think of how what tree, what SBA you should be looking at, it should be this. V star sitting at the root, its first log n minus L children have no reversed arcs incident on them, okay, because I know that inside they will not have anything, this, and the last L, these are allowed to be blue. So now the question is, what should I do? How do I fill up these information? Like who should go here to these sort of these subtrees and who should go to these subtrees? if there exists a solution, if there exists a solution to my original problem, then there exists a solution which looks like this. That's what this result tells me. So now can you tell me what I might do now? These are also, okay. So let's just look at this is what I'm claiming, okay. I'm given a digraph D, okay, and I have this values L and so on. I can decide in this much time to power this to power n and polynomial this much amount of time and polynomial amount of space, okay, if D contains a spanning L removed SBA, T rooted at, this should be B star. If I could do this, then can I answer my question? Then using this fact that this property, if I could, that algorithm tells me tells me the answer to this question. Does D contain a spanning L removed binomial arborescence rooted at B star, right? So because of this if and only if condition, if I can answer this question, I can also answer this question, right? That's the implication here. That if I could answer that the question about L removed binomial arborescence, then I can also, whatever the answer is, yes or no, is the answer to the original question whether D can actually have an SBA with L blue arcs rooted at B star. Okay. So now the question is, how do we do this? Okay. So I am not going to expect you to know this because it requires a this thing called okay, just to take a step back here and just to tell you more important than how precisely we solve it is is basically what's happening. So look, we were given a graph D, right, the Winlow's graph. We were always looking for a spanning subgraph. And the spanning subgraph had to have this nice property of the SBA properties, right? That's what we were doing all along, in the first talk as well as now. Now, in this second part of the talk, the question was slightly modified in that if the original graph does not have an SBA, right, then can I change some L arcs, the direction of it, and then does there exist an SBA, right? So I can reframe these questions in terms of a subgraph isomorphism problem. You have a host graph, like a big graph, and you have a pattern graph, and you're asking, does this pattern graph exist in this bigger graph up to relabeling of vertices? So what that means is up to isomorph. So is there a subgraph which is isomorphic to this pattern graph? Okay. Do you agree? Like, is that clear? Do you have any questions? So anyhow, any manner in which you can solve this subgraph isomorphism problem, I tell you, you can basically use it to solve this sort of a tournament manipulation problem. Okay, that's sort of the thing. That's sort of the thing. Okay. So I'm going to tell you there is a way of solving subgraph isomorphism. That it's like a black box we use. Okay. So we have a bigger graph G. Okay. And a subgraph, a pattern graph H, okay. Suppose H, do you know what a tree width is? Okay, never mind. Okay, I'm just going to state it in terms of a, so suppose that the vertices of this graph, okay, are colored, okay. You're using some number of colors, let's call it T colors, to color this, okay, so H is the pattern graph. I'm looking whether H has a, the subgraph isomorphism problem is, does G have an isomorphic copy of H, okay. Now, a further addition to this particular problem is the fact that the vertices in G are colored. So let's call this the coloring function, okay. So this is, say, that you are allowed to use T colors, okay, the vertices have been colored. So what you are looking for is not only a subgraph, isomorphic subgraph in G, a subgraph in G which is isomorphic copy of H, but also that the subgraph is colorful, meaning every vertex in that graph has a unique color, okay. So that is the question. Now that question can be, so suppose this is of size, so h is of size k, okay, g is size n. Suppose this coloring function is the unique, in the sense that every vertex actually gets a unique color, okay. So then automatically if you get a subgraph which is in G, which is isomorphic to H, then automatically it has to be colorful, right, because every vertex actually gets a unique color. So suppose this is the situation. Now for the specific, so in our case this big graph G is the D graph, okay. H is the patterned subgraph. It is the sort of the SBA that we are looking for. Can you tell what is it, what should this H be that will allow me to solve this problem? I'm basically trying to solve this problem, right? Okay. All right. So, okay, one other thing that, okay. So when this, let's just go back to the definition, otherwise, okay, this thing, okay. When I give you a, when I define an L remove binomial arborescence of T, the L remove binomial arborescence you get is unique. Why? Because T is a label tree. From that you're removing the last L, the edges to its L of its last children, right? So the graph that you get, the new graph that you get, that is L remove, it is isomorphic, it is sort of unique up to isomorphism. Meaning you can relabel vertices, but the structurally it is, it's unique, right? So that's sort of an important point here, okay? Otherwise that thing, I sort of realized I should make that point, otherwise it doesn't make sense. Okay, so now if I know that there exists for a given T, there exists an L unique, there exists a sort of unique T L removed SBA from T, that becomes my pattern graph H, okay. Now, if my pattern graph H is, if that, now see H here is basically for my, it's a spanning subgraph, meaning all the vertices are present, but some L arcs are missing, right? And also, so basically what is H? H is no longer a tree because some, it's a disconnected, it's a forest, like a forest is a collection of trees, right? So now, this subgraph isomorphism problem, this colored version of subgraph isomorphism problem for rooted cases where say G is a rooted tree and H is a rooted tree, and you want the roots to match to each other, meaning the isomorphic copies should be such that every sort of the root of H is maps onto the root of G, then that problem, like that question, is there a isomorphic, does G have an isomorphic copy of H which is colorful, that is every vertex has color, has a unique color, has a distinct color, sorry. That can be answered in time, sort of okay, tree. Okay, all right, let me just, this is the time complexity of this thing. This would, okay, this is not H, this is should be K. This is, yeah, so this is a K in our K, and T is 1 because tree with, what did I do? Okay, 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 okay. sorry. Okay. So, all right. So this is the running time of, I'll just, okay, let's just, this is the running time of the algorithm, which gives a colorful subgraph isomorphism, which maps root to root. Okay. So this algorithm, when applied to our special case, where G, the vertex set of G is the same as the vertex set of H. Okay. This is this colorful function is basically a unique coloring. So if I find a subgraph isomorphism, if I find a subgraph isomorphic subgraph in G to H where the roots are mapped to this, so the root of G is mapped to root of H, then basically that solves this question of colorful subgraph isomorphism. So now this graph H is a tree in our case, meaning it's a forest, of course, because there are some of these rooted thing and then there are these subtrees that are disconnected, right? So the set size is n, both of them G and n. This is the tree width, this T is basically the tree width of this host of this pattern graph H. For now, assume tree width is something that you know. For our case H, because it's a forest, tree width is 1. So basically, this for algorithm will yield a time complexity of polynomial in n. So it's basically this, which makes, well, this is basically the same thing as saying 2 to the power n polynomial in n. Okay. So basically this one requires you to know some algorithm which solves subgraph isomorphism. That's what we basically used here. So essentially this is where the whole thing is, this property. Once you know this and the fact that having an L-removed binomial arborescence uniquely sort of determines the tree that you're looking for, that basically yields this algorithm. So this is the, so it's the L removed binomial arborescence, that is the pattern graph that for which we are looking for which we are searching for in the bigger graph G. Okay. Okay. So this basically solves, this gives an exact exponential time algorithm. Now remember, we actually started off with saying so anyways, so because we can solve this binomial arborescence, doing a little bit of more work, basically we know how to, that the L removed arcs would be adjacent to the vertices which are not currently connected to R. So basically solving this will give you, will solve the sort of the original problem, which is that tournament fixing with L arcs reversed. Now, we started off with the goal of finding an algorithm with time complexity k log k and polynomial in n, right? So we didn't actually forget that. So now, sort of, this is probably harder to see, but okay, let's just try and do some sort of some amount of intuition, like let's see why this might be true. Can you say, given that we know how to say find, we have that characterization of this L removed binomial arborescence, can you use that to give an algorithm to determine whether the given problem, the given instance actually has a SBA rooted at V star with L reversed arcs? Okay, so if you remember what we said, okay, this says k square log k, this any problem, so basically this is the result, this is the time complexity you would get if you use one of the earlier algorithms for the TFP problem that we discussed in the previous lecture. So we basically, what we do is, the way, we did not discuss the greedy algorithm, but that can be modified. Instead of solving this problem, that seeding problem where none of the arcs are reversed, we can change, slightly modify that algorithm if you, and instead solve this L removed binomial arborescence problem. So instead, so actually what is happening is that we are now looking for, we know that the L reversed arcs must be the last L arcs that are adjacent to, that are incident on the root, right? So those arcs are the missing arcs, those are the blue arcs. The rest of the SBA is actually complete. Do you agree? So therefore, by slightly altering the algorithm from the earlier in the morning, we can actually answer this question. Does there exist an SBA where only the L arcs rooted at V star and all those things, where only the last L arcs are reverse, like L arcs are missing, no reverse, nothing, we just don't have those arcs. So basically it's almost, this is why L removed binomial arborescence. It's almost a binomial you are almost like solving the original problem that we did in the morning with just some L arcs removed. So you can sort of think that, okay, these arcs exist, whatever the direction you need to give them in order for V star to win, you basically do that. So if you can, once we have that characterization property involving the L removed SBA, we can basically solve all these problems. Because the main, essentially the idea is, we know exactly which L arcs to reverse. They are the last L arcs. Okay. All right, so I think this was all I wanted to say when it came to the technical part. So I'll just conclude by saying that the tournament, this is one version of the tournament fixing problem, which is like the manipulation aspect, like you want somebody to win, how can you force that person to win, and so on and so forth. It's, there are other notions of tournament fixing. For example, if you did not care so much about who was the final winner, but instead you wanted that certain players will play the last round, like the final round. For example, I can tell you in this World Cup, Pakistan is already out of the running. If India and Pakistan played the final, 1 billion people would watch. That is like greater television rating than, like, I don't know, 500 Super Bowls and like NBA, all of them combined. So if a tournament organizer could do that, that would be fantastic for them. So, you know, you can think of a problem like that. I don't care so much of final, but I care about who appears in the last few rounds of the competition. Like, or maybe you want, okay, so this is where the winner is this. So there can be other questions also if you are interested in this. For example, suppose if winning is not an issue, these teams are playing against each other, they have to go to each other's home arenas to play, the distance is very large, okay. So you don't want one team to have to travel a lot, right, going to somebody else's arena and coming back and so on and so forth. Suppose what you have in hand is you are a tournament organizer and you have is the distance of the home locations of all the teams, right, and what you want to do is sort of minimize the maximum distance traveled by any team, and you want to create a seeding, right, the the pathway to the final thing. You don't know who will win which round, but the point is whoever wins, no team will have to travel more than a certain X amount of kilometers. So you can basically change your goal, right, and still ask various types of questions in this tournament setting. Like you can change your objective. Here the objective was who is winning and why, like, and so on and so forth. How can we find the winner and all. In other cases, you can have other imperatives and sort of that thing. And of course, the basic underlying model can also change. We had a complete directed graph telling us what the various matchups will be. That's the graph that we were working with. You may have a probabilistic graph. The edges are basically probability values. So more than half, like whatever the probability value is, both direction edges exist. They add up to 1 and so on. So then the question would be, what kind of seeding would maximize sort of the probability of my player, my favorite team winning, and so on and so forth, right? Okay. So, and these are all cases when you have the complete binary tree. So there can be other instances in which sort of not everybody has to play every round, your initial rounds are bi and so on and so forth. Okay, so the structural properties are interesting for me personally. I like studying the structural properties because they actually inform the algorithm. Because just a lot of general algorithm, like if you don't understand the structure, you cannot hope to find good algorithms, in this case efficient. If you understand the structure, well, there are lots of structural properties one can still think of, and then you can use that to design algorithms, okay. And this, the number of upsets was one parameter that we talked about. It seems a reasonable parameter because, as I said, the number of upsets can always be expected to be a lot less than the number of matches played. But of course, you can come up with your other parameters that you want to, that you think would always remain small. This is a particularly important thing when we are dealing with NP-hard problems, when you're looking for, cannot expect to have a polynomial time algorithm, so then you're trying to settle for the next best thing. Okay, all right, so I think I'll stop with that. Thank you.